let's see some major performance parameters for a standard second order control system. First, let us assume the input is a unit step signal. By putting the value of Laplace transform of the input 1 by s, we can easily find the Laplace transform of the output. First, we will do the partial fraction, and the next step is the most important step in finding the output expression in time domain, which is actually rearrangement of the denominator. All this rearrangement procedure is being done just to convert this Laplace transform expression into the Laplace transform of basic signals like cos and sine signals. After taking inverse Laplace transform of this expression, we can easily find the output expression in time domain. We can simplify this expression by using a very common trigonometric identity, which is a sin t plus b cos t is equal to under root of a square plus b square multiplied by sin t plus tan inverse b by a. By using this, we will get another expression for the output signal in time domain, and finally we will be having this expression for time domain output signal, which is equal to 1 minus Euler's number raised to the exponential minus zeta into natural frequency multiplied by time t divided by under root of 1 minus zeta square multiplied by sine damped frequency omega d multiplied by time t plus theta, where theta is equal to cos inverse of zeta. This is the same angle which we have seen in the previous lecture, which is actually the angle between the negative real axis and the line joining the pole with the origin in the S-plane. As you already know, we are having 4 cases, but here we will first consider the case of underdamped system, because there are 2 major reasons why we are considering this case first. The first is this case is actually desirable case for our applications, and also since the value of zeta is very specific in case 1 and 3, they will not give general formulas. But in this case, since the value of zeta is a range, that's why the formula which will come in this case are general in nature. We have seen how the unit step response of underdamped systems looks like. This output profile will actually help you in giving more insight of different performance parameter which we are just about to study. The first performance parameter is the rise time, which is the time needed for the response to reach from 0% to 100% of the desired value of the output at the very first instant. Desired value simply refers to the final steady state value. You can also see there are multiple points of time where the output response reaches its final steady state value, which is 1, but the time when it reaches its final steady state value for the first time is the only time which is considered as a rise time. Now let us try to derive the formula for the rise time. We have already derived the expression for output signal in time domain. Also, for rise time, we know the output value has to be equal to final steady state value of this expression of the output, which can easily be found to be equal to 1. Simply putting the value, we will end up with this expression. The denominator in this expression can be simply removed. The exponential term can also be removed, as there is no such value of zeta where this value will become 0. So, the only term which can lead the value of this expression to 0 is the sine term. Solving this sinusoidal expression, we will get damped frequency omega d multiplied by time t plus theta is equal to n pi, where n is any natural number. But as you saw in the graph also, there are multiple values of time where the output will reach the value 1. But for the rise time, we have to consider the first value of time when the output response reaches the value of final steady state value, which is 1. And that is the only time which you can say is the rise time. That's why in this expression we have to put the value of n to be equal to 1 to find the value of rise time. Finally, the rise time will come out to be equal to pi minus theta divided by damped frequency omega d. I hope you are concentrated not only on the formulas but also on the derivation of this formula along with proper definition of the parameter, because all these 3 things are important. Also, if a question comes about the derivation of any formula, then it will be much better if you derive the expression for the output response also, rather than simply learning and putting the value of the output signal in time domain directly. You should derive the expression for output signal in time domain the same way we have done it initially in this lecture. Now let us come to the next performance parameter, which is the peak time. It is the time required for the response to reach the first peak of the overshoot, which in mathematical language is simply the first maxima. The overshoot are the region of the response which is lying above the final steady state value, whereas undershoot is the region of the response which lies below the final steady state value. The peak time is being referred as TP, which is denoted in the graph, trying to give you a graphical idea where the peak time will be located. The first step of the derivation of the peak time is the most important step. Otherwise, the next steps are quite simple. As you know, the output at the peak time is having a maxima at that time. That's why the differentiation of the output response should be equal to 0 at the peak time. After simply differentiating the output signal and equating it with 0, and after cancelling the common expression, we will have tan damped frequency omega d multiplied by time t plus theta equal to damped frequency divided by zeta into natural frequency omega n. After simplifying this expression also, we will have tan omega dt plus theta equal to under root of 1 minus zeta square divided by zeta. If you observe carefully, the expression in the right hand side of this equation is actually equal to tan theta. You can actually check it yourself by putting the value of zeta equal to cos theta. So, after solving this trigonometric equation, we will have damped frequency omega d multiplied by time t to be equal to n pi, where n is any natural number. As you can see, there is a range of different values of the value n. And also in the graph you have seen there are many maxima as well as minima. The values of time for different maxima, we have to put the value of n equal to 1, 3, 5, 7, which are odd values. Similarly, for finding the different values of time for different minima, we have to put the value of n to be equal to 2, 4, 6, 8, which are all even natural numbers. But what about the value of peak time? Peak time, as you know, is the first instant of time where the response has a local maxima, and as such we have to put the value of n to be equal to 1. The value of peak time will come out to be equal to pi divided by damped frequency omega d. In the response you can see the first extrema is actually a maxima, and we have to put the value of 1 to find the time at which the response achieves this maxima. This time itself is nothing but the peak time. The next extreme point is actually a minima, which is denoted by the number 2. So, to find the time corresponding to this point of response, we have to put the value of n equal to 2 in the expression of time. The same way, we can find different values of time corresponding to different maxima or minimas, which are actually the extreme or peak values of different overshoots and undershoots. The next parameter is peak overshoot. The maximum positive deviation of the output with respect to its desired steady state value is known as maximum or peak overshoot. You can see in the output profile that we get the maximum peak overshoot at the peak time. The formula for finding the peak overshoot in percentage is equal to the value of response at peak time minus steady state value divided by steady state value multiplied by 100. We already know the steady state value in our case is equal to 1. Now we have to simply find the value of response at peak time. We are already having the expression of output response. We have to simply put time equal to peak time, where peak time is equal to pi divided by damped frequency. Putting the value of peak time in this expression, we will have another expression of response in terms of sine pi plus theta. A very simple trigonometric identity is that sine pi plus theta is actually equal to minus sine theta. By simply applying this identity, we can simplify our expression further, as you know already that cos theta is equal to zeta. So, under root of 1 minus zeta square is actually sin theta, so we can cancel under root of 1 minus zeta square with sin theta in the numerator. Now, our final expression of the output value at peak time will be equal to 1 plus Euler's number raised to the exponential minus zeta pi divided by under root of 1 minus zeta square. We have to simply put this value of response in the formula of peak overshoot. By doing so, we will get the maximum peak overshoot value to be equal to Euler's number raised to the exponential minus zeta pi divided by under root of 1 minus zeta square. The next parameter is delay time. It is the time required for the response to reach 50% of the final value in first attempt. The empirical formula or the approximate formula for delay time is equal to 1 plus 0.7 multiplied by zeta divided by natural frequency omega n. The time will come in seconds and we have to put the value of natural frequency in radians per second. Before moving forward, I think you should try to solve a question so that you can check whether you are actually understanding the concepts or not. Since you have to find the delay time of the system, your first step should be to find the steady state value, which will come out to be equal to 3. Now, as per the standard definition of delay time, it is the time required for the response to reach 50% of the final value. So, we have to equate 50% of the final value to the expression of output to find the value of delay time. By solving this expression, you can find the delay time to be equal to natural logarithm of 4 divided by 3, the whole being divided by 4. This will be the answer. The point which I am trying to teach you here is that it is not necessary that you have to solve problems by using formulas only. Many times, the question will check your knowledge about the definition only. It may be possible that there is no need to use any formula at all. That's why I told you earlier also that definitions along with formulas and their derivations are important. Don't ignore any of them. Now let's see the next parameter, which is settling time. It is the time required for the response to reach and stay within a specified 2% tolerance band of its final value. The approximate formula for settling time is equal to 4 divided by zeta into natural frequency omega n. This formula is meant for 2% tolerance band only, and if we have to find the settling time for 5% tolerance band, then the formula is equal to 3 divided by zeta into natural frequency omega n. For an underdamped system, the magnitude of the oscillations present in the output time response decay exponentially with a time constant of 1 divided by zeta omega n. As we have seen earlier, the definition of time constant that it is the time at which the response reaches 63.2% of the final value. But here, as you can see, the response first increases, then decreases, then increases again, and the sequence will keep on going like that. Here, the time constant is not representing the rise or decay of the output. It is actually representing the decay of oscillations. I have tried to represent it with red dashed line in the output profile also. Here, the time constant is used analogically only, which represents the decay of oscillations, not the output. It is quite strange that by using only two variables, we are having so many parameters. By using damping ratio and natural frequency omega n only, we are having damping factor, which is zeta into omega n. We are having time constant, which is equal to 1 divided by zeta into omega n. And we also have the formula for settling time, which also contains only zeta and natural frequency. There is one more point which will help you to understand how to answer theoretical questions. We have seen 5 parameters and 2 of them are rise time and peak overshoot. The formulas we have already seen. Now try to think logically. What value of rise time is desirable? Should we have a very high value of rise time or a very small value of rise time? If you turn on a fan, obviously you would want the fan to give cool air as soon as possible. Even when you turn on any signal, when you initially start the system, it does not respond instantaneously. It may take time, maybe in milliseconds, but still it will take time, so that the system can recognize the voltage to respond accordingly. Eventually, everywhere we need our devices to respond quickly. That's why small values of rise time is favorable. Now if you try to think the peak overshoot, then here also try to assume that you are having a device whose voltage value rises quite high. Obviously there is a chance of over voltage which will lead to high level of heat dissipation which can damage our devices. So here also small value of peak overshoot is desirable so that the high value of voltage or current does not damage our devices. Now let us try to find which value of zeta is favorable for having a smaller rise time. We have substituted the value of theta which is equal to cos inverse zeta, and also we know the damped frequency is equal to natural frequency multiplied by under root of 1 minus zeta square. By hit and trial method, you can take any two random values of zeta like 0.2 and 0.5 and can check which value of zeta will give a smaller value of rise time. After doing that, you will get to know that a smaller value of zeta is actually favorable for having a smaller rise time. Now let us see the case of peak overshoot. The same way, by using the hit and trial method and taking any two random values of zeta, you will find that the bigger value of zeta is favorable for having a smaller value of peak overshoot. But unfortunately, these two statements are contradicting. And when this happens, we usually have an optimum range of zeta so that we are giving equal importance to both the parameters so that the device works best after compromising with both the parameters. Now consider these three statements and answer which of these statements are true. The first and the second statement is obviously false. As we just saw, there is an optimum range and we don't want the value of zeta neither very low nor very high. Third statement is actually very tricky. It says to have good maximum peak overshoot performance, a standard second order control system should have zeta as close as possible to 1. This statement is actually true. But if such statements appear in exam, then obviously first you have to decide what does the good in this statement mean. You have to judge yourself what value of maximum peak overshoot can be considered as good, whether the value should be small or should it be large. And also, since in this statement only one performance parameter is considered, which is maximum peak overshoot, then obviously you have to ignore all the other performance parameters. If you are confused about other parameters and what should be the ideal value, then let me tell you, the ideal output profile should look exactly like a unit step signal. And a unit step signal has all the parameters which we have studied in this lecture equal to 0. Rise time, peak time, maximum peak overshoot, delay time as well as settling time all should be 0. These are the ideal values, but remember, for getting these ideal values, we may require different values of zeta. Try yourself, consider different parameters and determine which value of zeta is favorable to have smaller value of that parameter. It will be pointless for you if you move to the next lecture without having proper understanding of this and the previous lecture. The next lecture will be dependent on this lecture as well as on the previous lecture.